quickly detecting, identifying, and monitoring crop disease and pests. According to the UN, growers
Test. Hi, thank you for joining us at Open World 2019. I'm going to be talking to you about a lot of exciting emerging technology today. This presentation is about the use of emerging technologies like AI, drones, IoT, big data, and Oracle cloud-native services, including Kubernetes, containers, in specifically for agriculture. We're going to start you off today with a quick video of the company that Oracle Cloud has been working with, AgroScout.
AgroScout is revolutionizing field crop scouting with its autonomous, cloud-based artificial intelligence system for quickly detecting, identifying, and monitoring crop disease and pests. According to the UN, growers lose 20 to 40% of crops to disease and pests, and manual, sample-based scouting doesn't provide full coverage. Existing remote sensing techniques, which have been developed in recent years to address irrigation and fertilizing, are not sensitive enough to accurately detect diseases and pests on time, even when incorporating satellites, planes for scouting. AgroScout's autonomous system uses off-the-shelf drone and camera technology to scan entire fields at minimum cost from the first acre. Integrating weather and other data from existing sources, our highly affordable solution harnesses artificial intelligence to speed up plant-level scouting and to pinpoint the affected areas and recommend treatment. By providing early detection and identification of disease and pests, AgroScout's comprehensive system reduces scouting expenses, optimizes chemical pesticide use, and has the potential to significantly increase both crop quality and yield. Join our scouting revolution, AgroScout. Detection done right. Go to agro-scout.com to start saving today.
So hopefully that gives you an idea of what AgroScout does. So Simcha, could you tell us a few words about yourself?
Yes, good morning. My name is Simcha Shor. I'm from Israel. I just flew 15 hours to be with you, so I'm honored, and it's a great pleasure to be here with you. And it just shows us how small the world is becoming. Not only is it becoming smaller, we have more people that we need to feed. I spent the last 20-some years developing technologies in the defense department, and in the last 3 years trying to take those technologies of remote sensing, computer vision to the agricultural world.
My name is Akshay Parthasarathi. I work with cloud native services in the product marketing team at Oracle Cloud. I've been working with the computing industry for over 10 years now. I've been with some well-known brands as well as startups, including Amazon Web Services.
Supposed to go on?
You're supposed to move on with this.
Yes. All right, so let's just look a bit back to how we're using technology in agriculture. It's not something that we started. If we look back to ancient times, to ancient civilizations, we see the Egyptians, the Greeks, the Persians, they all tried to master time, to master the times of the year. These are cultures that are agricultural societies. They need to know when to plow and when to seed. they have no idea what the time is. They don't have calendars and things like that. And what's unique here is the Antikythera mechanism, which if you haven't heard of, I strongly recommend looking at this on YouTube. This is the most ancient mechanical computer in the world, probably more than 2,000 years old, built by the Greeks. And it allowed them to see the times of the year, to follow all the planets, things like that. Obviously, probably also for religious reasons and things like that, but also for the times of the year. And this is the first time where they're capturing knowledge in a machine to help them with agriculture. If we look at the evolution, revolution in agriculture, we see a graph of the population of the world, which didn't really grow too much until the 18th century. But since then, we see more and more people, and we see more and more agriculture. We see revolutions in chemicals and machinery, all the way up into the 50s and 60s, where we introduce fertilizer and pesticides and tractors, which allow us to increase dramatically the amount of crops in the world. And that is actually what's been feeding the world for the last 50 years. But we've actually reached a limit in the amount of what we can grow. If you look at rice and wheat and, what am I missing?
Corn.
And corn, the three major crops of the world, we're at the limit. For the last 10 years, we haven't really changed the amount that we're growing. And these are things that have drawn technology in the last 20, 30 years into agriculture, namely called precision agriculture, which is trying to go from a more statistical kind of treatment to a more almost plant-level treatment. And we see all kinds of new technology in this area. In the last 20, 30 years, we see remote sensing, taking images in the near and infrared spectrums from satellites, from planes, and now also from drones, giving us data that we didn't have before that. But now, because we're at that limit and we need to grow much more, we're actually looking at the next revolution in agriculture, where we need to grow almost twice as much as what we're growing now. We'll have another 2 billion people in the next 30 years, and we need to feed them. And that is going to happen through robotics, artificial intelligence, and cloud computing, like we'll show that we're doing through Oracle's cloud. I think this is over to you.
So similar to how there has been an evolution in agriculture, there's of course been an evolution in computing as well. So in the beginning, in the 1800s, we had the first computing machine created. That was by Charles Babbage. And then after that, Alan Turing in the 1930s created what he called the Turing machine. So the Turing machine was the very first implementation of a CPU, if you will. We've then had hardware enhancements. The ENIAC developed, the press seemed to call it a giant human brain, if you will. And then the invention of programming languages, the invention of computer chips or integrated circuits, and then software enhancements after that. So, things like the development of Unix, the first PC with the GUI, which is the Apple Lisa, and then the development of HTML, which is underpinning a lot of the internet today. So all of these, if you notice, what has happened is there were a number of enhancements in hardware, and then in the more recent past, there have been a number of enhancements with software. So if I can just continue in that theme, in terms of enhancements in software in the recent past, if you look at the 1970s, a lot of the implementation, the user's responsibility was everything from the hardware up. So the operating system, the runtimes for the languages, the containers, if you have them running, and the code. That's not to say that physical machines cannot be used anymore. There are very good use cases, including HPC for physical machines. But after that, in the 1990s, we had the VMs come up, abstracting out the hardware from you, so the operating system, the runtimes, and the application containers and the code are your responsibility. And then going further out, into the 2010s now, we've had containers and functions come up. And what these are doing for you in the case of containers is they abstract out the language runtime for you. And in the case of function, they even abstract out the containers. So you just bring the code that you need with functions, you run the code. You don't even need to deploy your containers or manage them. This presentation is about a lot of emerging technologies, and you're going to see a number of different things that AgroScout is using. One of the technologies is artificial intelligence. Um, Simha's company has been using AI to track diseases in crops, crops affected by pests and so on. And this is all done with image recognition using AI technologies. The images are captured with IoT devices, drones, which scout the field. Scouting is just like going around the field to identify any problems.
Yes, we're actually using these small commercial robots that cost maybe $1,000. Maybe a few years ago, countries used to have these kind of capabilities. Today, there's several companies building these for $1,000. Great cameras on them, allowing us to capture imagery like never before.
Right. And then this other part of it is, of course, the software stack. The software stack is all running on Oracle Cloud Native Services. They're leveraging containers, build pipelines, and I'll talk to you more about how they're doing that too. In addition to all that, as you can imagine, when you go through the fields, scout the fields with drones, and you have these images to analyze, you need some way to store these large amounts of images that have been gathered for you. So it's a big data problem as well.
Yeah, so at the end of the day, this is a journey about food security. Like I spoke about before, we need more food to feed another 2 billion people. And when we look at the details here, the UN is saying that we're losing 20 to 40% of crops every year. That sounds ridiculous at a time that we need to grow more. But when you look into these figures, you actually see it's even more. In some countries, it's even 50%. At the same time, we see more and more use of chemicals. Obviously, that's not working because it's not reducing these numbers. But we do look in countries like the US and Israel and other countries that are doing something called scouting, where we have a professional person walking in the field looking for these diseases and pests. It's actually reduced to 5 to 10%. The only problem is there's about 1 billion acres of field crops around the world. We don't have that kind of manpower to walk those fields. And this is where robotics and AI and cloud computing come in to help us.
So if you will, there are 3 levels of AI. So the first level is AI performing simple human tasks. In this case, for example, we want an AI to identify the numbers in a number plate. So these are things that we do intuitively. The second level of AI is machine learning. In this case, what happens is there's a human assisting the AI in doing some kind of pattern recognition. For example, if you're wanting to identify human faces, a human being would teach the AI that the eyes, the nose, the mouth, the ears, and so on make up a face, and the AI can subsequently use the machine learning algorithm to identify human faces in other pictures. Now, the third level of AI is deep learning. So with deep learning, the algorithm itself is sufficiently advanced to learn on its own. So what's happening is you feed in these massive data sets for it to do some kind of pattern recognition. In AgroScout's case, to do the recognition of diseases in pictures of plants that are collected. So deep learning is the algorithm learning by itself, the third level of AI. Now, in terms of how AI is actually affecting your organization, it's pervasive. It can affect many different functions, if not all of them. You can take a simple example of, let's say, you're wanting to process expense reports. The analysis of expense reports, and then subsequently accepting or rejecting them can be done with an AI algorithm that can recognize patterns for you. There are also other examples. AI can be used to screen resumes, for example, in your HR department. So many different use cases for it. It's also applicable across industries, and that's what I show over here. Now, looking at some examples of AI, if you use Netflix, you have recommendations that are provided to you every time you log in. These are generated by analyzing your past viewing history and comparing it to other users using AI algorithms. Uber, the routing of the driver to you by Uber or Lyft, and your route that is taken to reach to the destination is all done using AI. Many, many more examples, the use of self-driving cars to identify objects on the street, navigate appropriately, and so on. The use of AI in financials, so to make recommendations on what stocks you should buy. So all other examples as well.
Let's talk about this in agriculture. Agriculture is a bit slower than other industries. It's a very conservative kind of people and things. And there's a reason for that, because we lost the presentation. There's a reason for that because these people are working very hard and are making less and less. It's less and less profitable to be a farmer in this world. So they're not so quick on adapting new technologies unless it's really showing something that's helping them. On the left here, we see a very interesting company called Moscone, also an Israeli company. They built a robot that drives around in tomato greenhouses. Apparently, we lack manpower to pick tomatoes. It detects the tomatoes using computer vision and AI and picks the ripe ones. At the same time, we're also taking images to detect disease and pests. And on the right, FruitSpec is doing something similar, but in orchards. Apparently, orchards, they sell the apples to the supermarket or the processor at the beginning of the season, and they never really know how many apples they're gonna have. It's usually like they just look at it and say it's gonna be a few tons, and they're usually off by 30, 50%. What this system does, it drives around in the beginning of the season, and when the apples are still very, very small, it's able to see all the apples and count them and say how many tons there'll be in that orchard. I have to come closer. Yes. The biggest challenge now for using this kind of information in agriculture is the amount of data that we're collecting. If you're familiar with Planet Labs, it's a satellite company that has 120 satellites in a ring around the Earth. They cover every inch of the Earth every day. They're using this for all kinds of stuff, but if you look at this for agriculture, it can help us see what kind of fields we have globally and when, and how are they doing. The resolution isn't that good yet, but it's just getting better and better. And there are many other satellite companies. And if we look at the amount of hundreds of planes flying over fields collecting data, and now there's about 3 million drones out there, and that number is just gonna double and just explode in the next few years. Just 1 million of them just in the US. They're not all in agriculture, but quite a bit of them are in agriculture also. And also if you take into hand 1 billion phones that farmers actually have and take images of problems when they have in the field. But we don't really have any people that can look at all of this data. It's just endless. So here you see why we need deep learning. When you're looking at that license plate, or even a facial recognition, it is something that we can train the algorithm to look for something. Nose, mouth, distance, that's a face. License plate, numbers, that's a license plate. In this case, and you need thousands of examples to show the algorithm before it knows how to do it by itself. In this case, we have thousands of images of the disease, but each one looks different for us. So if for us, each one of these pictures look different, and they're all the same disease, if we have a scout or an agronomist in this room looking at this, he will just tell us it's all the same disease. But when we look at it, it looks very different. And that's where deep learning comes in, because we just feed the algorithm thousands of images of disease and tell it this is this disease, and the algorithm is seeking patterns by itself. Size, shape, place on the leaf, things like that. Trying to imitate the way our brain works when we're looking at something like this.
And what Oracle has been doing is, of course, if you see in the calculation here, you need approximately 550 petabytes of data of storage a year. This is object storage. And Oracle has, of course, a global footprint. to support this kind of data at the appropriate data centers in each case. So you could have fields in Australia, you could have fields in Asia, Africa, and so on. So supported in the appropriate data center. In addition to that, there's also vast amounts of computing power that is needed for the deep learning algorithms. So the use, in AgroScout's case, the use of the GPU shapes, GPU instances, has been helping them with actually the compute capacity as well.
So this is what's basically happening today. In a few, very few of those 1 billion acres around the world, we have people that are walking in the field. This is like maybe 100 acres. They see a very small part of the field, and that's how they decide what chemicals are going to go out on that field. It's like taking one person's temperature in this room and giving everyone antibiotics. It might help another person in the room, probably not. That's the case in agriculture. That's why we have more and more chemicals not doing anything. At a time that we actually want to reduce chemicals. American growers have trouble selling their crops to Europe because in America you're allowed to use more chemicals than the EU is willing to accept. So now American growers are looking for ways to reduce the amount of chemicals, not because they want to get rid of chemicals, but because they want to be at least okay with the EU or other things. And at the same time that this person is walking maybe for 20 minutes in a field, he'll see 100, 200 plants, and he's great at 7 in the morning. By 8 or 7 in the evening, he's tired. He's not really looking at plants at all. At the same time, we use the small drone. This drone has a 20-minute, 30-minute battery flying 10 meters a second or 30 feet a second and taking images around the field like in checkers. Very low, so the props are turning over some of the leaves. Pests are usually on the bottom side of the leaf. They're not on the leaf. So remote sensing from planes and satellites and drones that fly higher just don't see pests, and that's a major problem. But this actually turns over the leaves. We get images of the bottom part of the leaf where we see the pests. At the same time, we're getting hundreds of images, and each image has 10 plants. It's thousands of images of that field. And all those big images need to be processed somewhere in the cloud. Here you see on the bottom, it's a drone taking an image of the drone. You see the drone flying around by itself. It's imitating that W pattern that a scout would walk in the field, and it's taking an image about every 2 seconds. If you look closely now, you'll see how it turns over some of the leaves. Depends on the height. We usually fly maybe 3-4 feet above the crop. This is a potato field up in Washington. Yes, so now it's finished. So like I said, it'll cover maybe 100 acres in about 20 minutes, taking hundreds of images of thousands of plants, millions of leaves. We don't have people that are going to look at all those pictures. So we look at a lot of field crops. We look at crops where there's a correlation between the visual agronomy and something that's going to help the grower grow more, make money. If it's something that if we detect and the grower's not going to have anything to do with it, we don't really look at that. And there's some things that we just can't see. Some things you need to open up the corn cob to see. Something you need to take out the potato from the ground to see. We're not going to be able to see that. But it's much better than nothing. And again, most of the billion acres in the world have no scouting, and they're losing 30, 40, 50% of their crop. Obviously, grapes is not a field crop. It's a fruit. But if you're flying over it, it looks like a field crop. And this is an example of how we train the algorithm. So we spend a lot of time taking images over fields, but we use so much chemicals, we don't really see any problems anymore. So in this case, we're growing fields and not treating them for a specific disease or pest. In this case, the beetle, and now we have thousands of images of the different stages of this beetle. And once we make all those little markings of it, now the algorithm knows how to do it by itself. And it'll be able to find even one beetle in a real field. This is a real field, but it's not treated for the beetle. This is an example where we want to lower the amount of chemicals, and we can only do that if we're doing high-level monitoring. So this is what we'll be doing next season. We'll be doing a lot of monitoring with this and using less chemicals against this beetle. Short video.
All right, so we're here in Pasco.
That's a potato field.
Alan Schreiber and I are going to talk to you a little bit about potato pest and disease. So potato production, there's a lot of acres and a lot of big fields, and scouting is a pretty intense and expensive endeavor for growers. But also applying crop protection materials are also expensive. So in the way the economy in growing crops is now, the margins are really tight, so growers can't overspend on chemicals or scouting.
So we're working with AgroScout to develop a significantly better way to quickly and cheaply scout their fields, and we believe that the AgroScout technology has great potential to reducing the cost of potato production and improving pest management of insects and diseases in potatoes.
So many pests and disease, if treated early or when there's very few, like for instance with early blight, when there's few lesions in the field.
Just look in the back
or
what a
with
potato
beetles,
field
when
looks
there's a
like.
small population,
It's
treating them
endless,
is more
endless,
effective when you
millions
start when
of
the population's
leaves.
small than when the population gets out of control. So we hope with a technology like this that many acres can be scouted. These small occurrences can be found in fields before they evolve into larger populations that could be more damaging to the crop.
So this is basically how it's done. I'll just hand over in a second to understand the tech about it. But it's about using commercial, low-cost robotics, very simple. Just put it in the corner of the field, our app will fly it around by itself autonomously. All the images, or from your phone, all the images go into the Oracle Cloud anywhere. When we started, we were using other clouds, and the images going up from Brazil would take an hour to get up to where our cloud was. Now, with Oracle, it just goes up into that Oracle Cloud in that specific place. The analytics, which is a major part of this, is very computing using. That also happens in the cloud. And that's the resolution that we get on the right. It's a 0.5 millimeter pixel. It's better than what we see with our eye. So when we look at something next to you, that's how good the images are. It just means they're very big images, and it's a big deal to upload them somewhere, store them, and do the analytics on them. We divide each image into 60,000 squares that the AI is running through. So think of how many processes are happening on each image, and there's hundreds of images just on one field.
So in terms of, how Oracle Cloud is helping with all of this. So as Simha mentioned, there are these drones that are actually collecting data from the fields and sending it to Oracle Cloud. So there are two sets of services that are being used in order to store the information and also analyze the information. The first is the fully managed services. These are the services from the cloud native portfolio from Oracle Cloud. So in particular, they're using the container engine for Kubernetes, the cloud infrastructure registry, and the container pipelines. This allows them a way to deploy their workload fast. So they've gone down from 24 hours to only a few minutes for deployment. And then it's also helped them innovate faster, because if you can deploy faster, you can also you can have software development happen faster too. You can iterate faster. They've also taken advantage of the interoperability and openness that Oracle Cloud Native Services provide. By using it, for example, with Bitbucket, which is a source code management system, a third-party source code management system. The second set of services that they've used are actually the GPU compute, the object storage, and notifications from Oracle Cloud Infrastructure. So from Oracle Cloud Infrastructure, these services, in particular the GPU compute, provide a massive non-variable performance, right? So these are non-oversubscribed resources that can provide guaranteed performance for them to process the data and gain insights through deep learning. As Simha mentioned, there's also the global footprint that they're taking advantage of. Process the data closest to the field that is being analyzed. In addition to that, of course, you need a way to manage the infrastructure, and Oracle has the tools through Oracle Cloud Infrastructure Monitoring and also through the Management Cloud. So these are some of the results that they have seen so far. So in terms of performance improvement through the use of the GPU computes and the object storage, 30x in terms of that performance. And then some of these functions within their app, the mobile app and the web app, weren't even working before, and now they only take a few seconds. 24 hours to less than 10 minutes for deployment time. This is deployment time for new versions of the web app and mobile app. And then dynamic scaling. So as the technology gains more popularity, they expect exponential growth. So you need to have that ability to scale. So at a very high level, what AgroScout has done is they've taken care of the entire lifecycle management of their cloud-native infrastructure. So they're going from the deployment of the infrastructure, the first step, to the building of the application through a continuous integration, continuous delivery system, the use of image repositories. This is the Oracle Cloud Infrastructure repositories to store your Docker images. The use of container orchestration, Oracle Container Engine for Kubernetes, to run these workloads either in production or in dev test. And then messaging, telemetry, notifications, alarms through the use of Oracle Cloud Infrastructure and the Management Cloud. So here's the overall architecture diagram about what's going on with AgroScout. So typically, when there's a new version of the app that needs to be published, the developer is going to push it to the Bitbucket repository. The Bitbucket repository is going to, in turn, trigger a build through a continuous integration, continuous delivery product from Oracle called Container Pipelines, also known as Worker. Container Pipelines will build a new container image. This is the artifact as a result of the build will be pushed into what we see in the bottom here, which is the Oracle Cloud Infrastructure Registry. And then we also deploy it into production, into Container Engine for Kubernetes. Once it's deployed into production, we have the ability to send an automatic notification. In this case, a notification is sent to the developers using Slack that the build has succeeded, or maybe if there was an issue, that there has been an issue and they need to take a look. Now, I should point out that they're also using multiple versions of code, one for dev test and one for production, and they have corresponding Kubernetes cluster, a dev test Kubernetes cluster and a production Kubernetes cluster to take care of the deployment seamlessly. Here's a quick demo of Oracle Container Engine for Kubernetes and Cloud Infrastructure Registry.
Today, I want to show you some of the cloud-native developer services that are available within Oracle Cloud Infrastructure. I've logged into the OCI console. On the left nav, you'll notice a menu. If I drop down the menu to Developer Services, I see two managed services, one for a Docker registry and one for a managed Kubernetes service. Let's quickly look at the Docker registry. Clicking on OCIR, which stands for Oracle Cloud Infrastructure Registry, I see the registry with a number of repositories and images. I can quickly look at one of these by clicking on a container image. Here, I see a Hello Earth image with metadata about the image, such as who pushed it and how long ago. You also get full visibility to the layers and any metadata associated with the image. Now, if I go over to clusters, I can show you how easy it is to create a managed Kubernetes cluster with Oracle Container Engine for Kubernetes, or OKE for short. I selected the clusters page in the console. I'm going to create a new cluster by clicking the Create Cluster button. Within the wizard, I see it's automatically naming it for me. It's automatically selecting the Kubernetes version. By using this Quick Create feature, I'm going to take all the defaults, including the compute shape, which in this case is a VM. Bare metal shapes are also available for you to use. If I scroll down and click Create, the Kubernetes cluster is created automatically for me, including all the associated VCN components needed, and even a ready-to-use node pool. So everything you need to get started is getting created now. As you can see here in the cluster information, the cluster status is creating. Now let's watch as it brings up 3 VMs that are the Kubernetes worker nodes where your containers will run. The cluster is automatically spread over 3 availability domains for a high availability. I can see now my cluster is active and that the node pool is starting to provision. Okay, I now see my node pool is active. All 3 worker nodes within the node pool, which is configured in a high availability fashion, are up and running. I can now go and access the cluster by using the kube config. Access to the kube config is available right here in the console. Just as simple as that, I've created a cluster and can immediately begin using it. Thank you very much for watching this demo about Oracle Container Engine for Kubernetes and Oracle Cloud Infrastructure Registry.
So we just want to show you a couple of screenshots of AgroScout's application.
So the different users, if I manage many farms, I will just see all the farms, all the fields all over. And if it's just green, it's fine. But if it has this little yellow thing above it, it means there's a disease and pest in that area.
And this whole application is running on Oracle Cloud.
It's all on the, yes. Oh,
So
next? Oh, I have to do the next. Yeah, so here it's showing you a specific field. Oh, we don't have the last one. Can we show the last one, actually?
sure.
One more slide. If you're an agronomist or a scout, now you can be serving someone from the Ukraine, can be serving someone in Africa, someone from South America, can be serving someone in Europe. He can look down into each one of these. Each one of these is an image. Each one of these is telling you if there's a disease and pest in that image and where it is in the field. It's hundreds of images. Most of this is happening by the algorithm. The algorithm is looking and detecting problems in the field. Some of them the algorithm knows already because we taught it. But there's so many disease and pests in so many crops, it's a journey that'll take quite a while until we get enough imagery to train the algorithm to do that. And just to close up, again, it's a journey about food security. In this time that we need to grow more, we should at least reduce the amount that we're losing to disease and pest. And robotics and AI, together with cloud computing, is allowing us to do this at a global scale.
So if you need more information, please reach out to me after the presentation. We have a free trial available to you and the always free tier as well. So you can find the information there. AgroScout also has a free trial. You can reach out to Sima at the email provided there.
Time is up, but if you have any questions, we're happy to answer. Questions? Yes, sir. Thank you. Thank you. Yes, sir. Yes. The labeling happens in two layers. One, we because there's so many disease and pests, and we don't have images of all those disease and pests, we train the algorithm how a healthy plant looks. We have a lot of images of how a potato plant should look, how a clean leaf looks. So the first thing the algorithm is doing is looking at all those leaves. If it's clean, it'll just throw that out. If there's something on it, it's then deciding if it's a disease or pest that it knows, or it's just bringing it up to an agronomist somewhere in the world to detect specifically what that is. Everything's in the platform. So any agronomist anywhere in the world can help any grower anywhere in the world. Welcome. Yes, sir. Yes. So there's 500 million growers in the world. I'd say our early adapters are ones that have internet at the farm. There's not internet in the field. Even here in America, in most fields up in north, there's no internet in the field. So it's about taking the images now and taking it back to the farm and uploading it. It's a process that they do today anyway. The scout, if he goes out to the field, they'll only spray that field the next day. It's not a real-time process anyway. So this way he brings everything back, and over a few hours it's up in the cloud, the analytics happens, and he still knows what to spray the next day. But the future is not spraying the entire field. The future is spraying just those areas in the field where you need. And the future is not waiting that day. Next generation of internet will just probably go right into the cloud. And then it'll all be much faster. Can we do what?
Yeah, we're looking
Yes.
into that right now, so sometime in the future.
I'm sorry, our time is up, but you're happy to talk with us outside. Yeah, they just went to throw us out. Can we
Okay.
just get a picture with you?
Yeah, absolutely.